I'm Jeff Hutchins. I work for Ranovus, and I'm here to represent the OIF as the PLO Working Group Co-Packaging Vice Chair. And today I'm going to talk to you about our work on co-packaging to standardize higher integration levels for next generation data center systems. So first I want to talk to you about the OIF. It's a group that identifies industry needs and gaps in specifications and standards. Then we develop implementation agreements or standards to address those gaps, and we perform interoperability demonstrations of those standards. We have quite a wide range of areas where we work. We work in optical specifications, co-packaging that I'm going to talk to you about today. We have a protocol track, a management track, an electrical interface track that works on the common electrical interface, and a networking track. It's a member-driven organization with 22 years of service, has over 120 member companies. It's completed 80 implementation agreements and done quite a few interoperability demos. The OIF's organized into a technical committee, which consists of these working groups that works on those specs that we just showed you. And the working group creates implementation agreements, which are the standards, and then the interoperability demonstrations for those standards. We also have a market and awareness and education committee group, which creates educational workshops and presentations like the one I'm giving you to here today. So let's talk about the motivation for co-packaging. So it turns out that there is an ever-increasing fraction of power dedicated to networking with the data center. And this is a problem because the total power to the data center is fixed. So the more power that goes into networking, the less that goes into computation. And it's the computation that you can sell as a service and pay the bills. So it's really important to try to keep a handle on this networking power. One of the ways to reduce the networking power consumption is to use co-packaging to reduce this electrical interface power. That's what we're going to talk to you about today, how that works. It's also important to note that co-packaging also enables new applications that wouldn't have been feasible with traditional methods. So the way we save power is shown in this slide. The first picture here is a pluggable or an onboard optics architecture. And you see the switch chip packaged on a host PCB, and then a front panel pluggable or an onboard optical engine device over here. And there's an electrical channel between the two, and in this case we use a VSR, a very short reach interface that the OIF's done. This could be an MR VSR link. Now, when we talk about co-packaging, what we've done is taken this optical engine, probably made it much smaller, put it onto a co-packaged assembly substrate, and you see now the switch chip is flipped right onto the substrate, so there's no package parasites in the way. So we have a very clean channel between the ASIC and the optical engine. And so this can be done with an extra short reach interface or an XSR interface that the OIF's defined. And this interface saves significant power in picojoules per bit over what you'd use in the first case. It's also possible that some of these optical engines will be larger than can reasonably fit on a co-packaged assembly substrate. And then in that case, we can put the optical engine out away and use a copper cable assembly, which has a very high quality electrical interface connection. So you can still use an extra short reach interface to reach it. And finally, we have what we call near packaging architectures. This is where we take the optical engine, but instead of putting it on the same co-packaged assembly substrate, we put it on a high density interconnect substrate. And then we have the ASIC has been packaged in itself, and that's placed on this board. And so we have a reasonably good electrical interface. The main difference is we have the parasitics due to the ASIC packaging. With this one, we can use an XSR plus interface, which has consumes a little bit more power, but allows us to support this configuration. And we're going to talk about that a little bit more later on. I like this slide that Microsoft produced. It shows the different co-packaging applications. I think it's worth a few minutes to go over these. So we've got three verticals. We have the data center networking, the AI training and machine learning, and disaggregation on the right. And if we look at these, you can see a variety of different configurations here, from electrical interfaces and optical interfaces. We have end nodes and switching nodes, which have different numbers of optical engines surrounding them. We also have different kinds of electrical interfaces. We have low latency ones and Ethernet interfaces that are supported, and then quite a range in application requirements. One in particular is latency, which is the microsecond and millisecond range for Ethernet networking, and down to less than 200 nanoseconds for the disaggregation side. So you see quite a wide range of requirements for these various applications for co-packaging. This one here is what we're going to talk about today. This is sort of the poster child application that everyone focuses on, and it's the traditional Ethernet switch chip. So this is what such a switch card would look like. So here you see the Ethernet switch ASIC in the center, and it's been flipped onto the co-packaging substrate. And around on this substrate have been placed our optical engines. And these optical engines have optical connectors on them, which are shown by the red dots. Now, these optical connectors connect to fiber, which can go to the front panel where the transmit and receive fibers would be connected to, as well as fibers going off to the external laser sources, which could be on an onboard configuration, a front panel configuration, or maybe a remote shelf configuration as shown here. It's also possible that the lasers are located inside the optical engines, so that these external laser sources would not be needed. If we want to take a look at how many fibers would be needed to connect up a card like this, I think it's interesting to take a look at this 51.2T Ethernet switch card with 100G electrical and optical lanes. We would need, for a DR configuration, which is 1 lambda per fiber, we need 512 TX and RX fibers for a total of about 1,000 fibers. In the FR4 case, where we're putting 4 wavelengths on a fiber in a CWDM configuration, we would need 128 TX fibers, 128 RX fibers for a total of 288 fibers total. So quite a few fibers in these systems. Now let's take a look at the laser source. So in the case where we would use a remote laser, we're studying a front panel pluggable form factor, and this is shown in this picture here. This configuration is very interesting because it's very easy to replace on failure. So if a laser fails, you can just plug this out and plug a new one in. This is important because lasers are typically considered the weak link in a co-packaging system. And so you have two ways. You can either have redundant lasers in the optical engine, or you can use a remote laser source. This particular form factor is interesting because it has a blind mate connector on this end. So when you plug it in, you electrically connect the remote laser source as well as optically connect it. So the kinds of things that would be in scope for the interoperability agreement would be the mechanical form factor, the thermal power classes, the electrical and optical specifications, as well as the eye safety requirements. And this just gives an example. The eye safety is really important because you wouldn't want anyone to get injured with the high powers that you would expect to get out of one of these laser sources. Now, another area that we've looked at is optical connector contribution to link loss. So I'd like to show you the top row, which deals with a front panel pluggable configuration. And for Ethernet, which typically we have a TP2 and TP3 compliance points defined for the signaling. With co-packaged optics, you'd have the same 2 compliant points, TP2 and TP3. Now, with the optical engine, however, before you assemble the optical engine, you want to make sure that it meets its specs. So you have another compliance point, which is at the connector that's on the optical engine on the transmit and receive side. Now, in the middle for the data center cabling, where you connect these two together, there'd be quite a few connectors in between here. And sometimes it's reasonable to convolve the loss distributions in these connectors. For instance, if one connector is high, another one might be low, and they can be balanced off. So you wouldn't have to add all the worst cases of the connectors together in that link loss. Now, in terms of the optical engine, we have this extra connector, as we mentioned, at either end, which increases the overall link loss. And it's unfortunate that we won't be able to convolve these loss distributions just because the compliance points are so close together, there isn't really an advantage, or just isn't possible to do that. Now, another topic we've looked at is connector loss and rework. So let's take the example that we have a connector that we're going to measure against some insertion loss limit, and it has a 0.1% chance of exceeding that limit on first chance mating. In that case, you would fail the test, which would mean you'd need to rework that connector, and you'd have a 99.9% first pass yield. Now, in the case where we have two optical connectors, both connectors would need to pass. That would be about a 99.8% first pass yield. That'd be about a 0.2% chance that at least one of them would fail, requiring some rework of the card. And in the case where we have end fiber connections, this is what the formulas would look like. And if we apply that to a 51.2 T switch card, you see for the DR configuration, we have a 66% rework rate, which means a 33% first pass yield. And in the FR4 case, we have a 25% rework rate or a 75% chance of first pass yield. And one other consideration that we won't spend the time to talk about today, though, is that whenever you rework a card, you always have the opportunity of introducing some latent damage, so which then could make the card unreliable during its service life. So these are all things that we're considering. Now, another interesting topic is how the optical engine and remote laser should be controlled from the host. So first, remember that we have two options here. We have a laser which is external to the optical engine and a laser which would be internal to the optical engine. And so therefore, there's really four possibilities here that we consider. So let's start on this side, where we would take this optical engine and remote laser source and make that look like a pluggable optical module. So the host would talk to the optical engine would communicate with the remote laser source, and that's how that configuration would work. And if the laser was internal to the optical engine, then from the host point of view, it still looks the same because the host talks to the optical engine, which has the integrated lasers in it. Now, the other approach that's being considered is for the host to talk directly to the lasers, in which case, as you see in this case, the host would talk to both. And if the lasers are integrated, then the host would talk to the same interface to deal with the optical engine in this. So the OIF is going to support both internal and external laser sources, and we're also addressing the management interface for the co-packaging. Now, with electrical interfaces, as we mentioned before, for the co-packaging, we're talking about an extra short reach interface. This has a 10 dB loss between the ASIC and the optical engine. But we're also working on supporting a near package configuration, in which case we would need to support a 13 dB budget, and that's what this XSR Plus interface is all about. And the OIF is supporting work in both of these areas. Now, let's talk about how co-packaging is being tackled by the OIF. So the OIF initiated a framework level umbrella project to study co-packaging last year, and we initiated then early this year, a 3.2 optical engine project to support that 51.2 Ethernet switching application. We also created an XSR Plus electrical interface project to support NPO, and we've initiated an external laser small form factor project to deal with remote laser source. And finally, we've created a management interface track, and within that, a CPO MIS project to deal with the management interface for co-packaging. So I hope you've enjoyed this presentation today, and thank you.